Hello class, in this video we are going to cover section 1.2, estimation, graphs, and mathematical model. In my table note, I briefly introduced what is estimation, why do we need to estimate, and how to estimate. In our book, we have two ways to estimate, rounding and modeling. Let's look at examples. To round a number, either whole numbers or decimal, we need to understand the place value of the number, of the digits in the number. As you can see, if we have a decimal, the decimal point is right here, then the place value of the digit to the right of the decimal point is a tenth, followed with hundredth, 1,000th, 10,000th, 100,000th, and millions. And to the left of the decimal point, the first digit to the left of the decimal point is ones, followed with tens, hundreds, thousands, 10,000s, and so on. We need to understand this chart before you round a number. Rounding is very important, especially for test 2. Test 2 covers personal financial management, and a lot of the questions require you submit the correct answer with correct rounding. So rounding is very important. Now let's look at this example. We are given a whole number. It's a very large number, 7,476. Actually no, it's 7,476,242,056 is a very large number. And part A, we need to round the number to the nearest 100 million. Well, let's see where is the digit that represents whose place value is 100 million. It's a whole number, right? So this is 1. This is 1. 100,000, 10,000, 100,000. This is 1,000, 10,000, 100,000. This is a million, 10 million, 100 million. 100 million is digit 4 place value. As you can see, the place value of digit 4 in this number is 100 million. So the rounding is going to take place at that digit. Well, to round the number to the nearest 100 million, we need to look at the digit to the right of 4, which is 7. Always look at the digit right behind, next to the place the rounding is going to happen. Since 7 is bigger than or equal to 5, we are going to round the number up, round it up. So round it up to 7,500,000,000. 1, 2, 3, 1, 2, 3. All right. So since we are rounding it up, so we change 400 million up to 500 million, and change all the other digits to zeros. So basically, we round 76,242,056 up to 100 million, and now 100 million add up on top of 400 million. We have 500 million right here. So the rounding result is 7,500,000,000. Second part, part B, is to round the number to the nearest million. Let me erase that. And let me double check I'm actually not muting myself. The previous video for this section has no sound, right? Because I muted myself when I recording. So yes, it is not, I'm not muting myself. Okay, so let's continue here. we are going to, part B, we are going to round the number to the nearest million. Nearest million, the digit is 6, right here. And again, we are looking at the digit right behind 6. So that is 2, right? That is 2. Since this 2 is less than 5, we need to round this number down. We are going to round this number down. Means we are going to get rid of the 442,056, changing them to zeros. So the rounding result would be 7,476,000,000. Means we ignore the 242,056. Change all the digits to zeros. Yeah. Part A is rounded up. Part B is rounded down. Let me know if you have any questions about this problem. How do we round a decimal? Very similar but different. As you can see here, when rounding the decimal part of a number, we drop the digits to the right of the rounding place rather than replacing with the zeros, like what we did earlier when we round a whole number. So instead of replacing with the zeros, we just drop them. The given decimal in this example is 3.1415926. Part A, round the number to the nearest 10,000th. Okay, so where is the place? This is tenth, okay? This is hundredth, thousandth, 10,000ths. This is a 10,000ths, all right? Yeah, tens, hundreds, thousands, and the 5 here is 10,000ths. So our rounding place is 5. And we look at the digit to the right of the rounding place. We look at the 9. Since 9 is bigger than or equal to 5, so we decide to round the number up. Round it up. So we have 3.141. So we round it up. So 5 go up to 6. And then drop everything else. Just drop the 9 to 6. Drop them. Okay? So the rounding result is 3.1416. We kept 4 decimal places to the right of the decimal point. And we round the number to the nearest 10,000th. Part B. Part B, we are rounding this number to the nearest hundredth. Again, this is 10th, the digit to the right of the decimal point. And hundredth is the second digit. Is this 4? Yeah, this is a hundredth. The weight or the place value is 1/100. So we are going to round this decimal at this digit. And we look at the digit to the right of that digit. We have 1. Since 1 is less than 5, we need to round this number down. How do we round this number decimal down? Just drop everything. Yeah. The rounding result for part B is just 3.14. Just get rid of 15926. Get rid of them. All right. Yeah. So when you round a decimal to the nearest hundredth, is equivalent to round the decimal to keep 2 decimal places. Keep 2 decimal places. And let's see this question. You and a friend ate lunch at a cafe. The check for the meal showed soup for $3.40, tomato juice for $2.25, roast beef sandwich $5.60, chicken salad sandwich $5.40, coffee's total $3.40, apple pie $2.85, chocolate cake $3.95. Round the cost of each item to the nearest dollar. When we work on the homework in assignment 1.2, please read the question carefully, especially the sentence in the parentheses. And in this case, in this part A of the question, we need to round all the numbers they are decimals, right? To the nearest dollar. And then add them up to find the bill of this meal. Okay, let's do that. So we should be able to do that in our head, right? Yeah. 340 rounded to 3. Tomato juice, 225 rounded to 2. Roasted beef sandwich, round up to 6. Why do we round it up? Because this 6 is bigger than 5, right? Chicken salad sandwich, rounded down 5. Coffee, rounded down 3. Apple pie, rounded up 3. Chocolate cake, rounded up 4. So let's count how many items do we have. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, we did not omit any items. So now we're going to add all those whole numbers together. So 11, 16, 16 plus 6, 22, 22 plus 4, 26. Let me double check. So this is 10, and this is 11. So 21, 21 plus 5, 26. Yeah. So $26 would be the estimate of the bill. The estimate of the bill. Part B, find the total bill, the exact bill. Oh, actually, it's given. The total bill before tax was given as 29.85. Is this amount reasonable? I think it's pretty reasonable. While our estimate is lower than the actual value. So this is, let me double check the result. So 3 plus 2 plus 6 plus 5 plus 3 plus 3 plus 4. So this make a 10, and this make a 11. So that is 21. 21 plus 5 is 26. It is 26. It is still very close, right? Yeah, the error is $3.85. Next question, a carpenter who works full-time earns $28 per hour. Part A, estimate the carpenter's weekly salary. Well, let's make sense. Let's say the carpenter, works 8 hours a day. Every week, he works 5 days, right? Take off Saturday and Sunday. So let's say the carpenter works 40 hours per week. Every hour he makes $28. Then how do we estimate the weekly salary of the carpenter? We're gonna use 28 to multiply by 40 to have the weekly salary for the carpenter, right? However, we wanna get this calculation done in head without using calculator. To make that happen, we wanna change the number or round the number to a convenient number. So instead of using $28, let's use $30. So if the carpenter's hourly payment is $30 and he works 40 hours a week, then his weekly salary can be estimated as $1,200. So 40 times 30, $1,200. Most of the people can get that done in head, right? 30 times 40, $1,200. So you don't have to use a calculator. You can just estimate the carpenter's weekly salary. Part B, estimate the carpenter's annual salary. So we already got the estimation for the carpenter's weekly salary, which is $1,200. And we only need to know how many weeks in a year, right? And we know there are around 52 weeks in a year. But 52 is not convenient. How about, let's round it to 50. Let's say we have around 50 weeks in a year. And then we use 50 to multiply by the weekly salary. You can get this done very quickly. 5 times 12 is 60. And then with this is 1, with this is 0, this is 0, 3 zeros. So the carpenter's annual salary can be estimated as 60 grand. 60 grams. Pretty good. Next question. So next questions are about graphs. We are going to see some graphs, pie chart, also called circle graphs or line graphs. When we learn statistics, we'll see more graphs. In this case, we just focus on rounding. You understand the graph and round the information that is given from in the graph. So let's read the question here. According to the Bureau in 2020, there were 249,019,818 Americans 25 years and older, assuming the given graph is representative of this age group. So this is the population we are in consideration. Assuming the given graph is representative of this age group, answer the following questions. Part A, determine a calculation that shows the number of Americans 25 years and older who define old age by a decline in physical ability. So to understand a question involving graphs, we need to take time to understand the graphs, right? This graph, is a pie chart. As you can see, the pie is divided into different sections with different colors. And this is 32% in green, 41% in blue, 14% in orange, and so on, yellow, and so on, right? So the total of those percentage must add up to 100%. And 100% should be the 249 million and so on, those population, right? So as you can see, 32% of those people who answer the survey think that decline in mental functioning defines old age, getting old. And 14% see old age as reaching a specific age. And 1% don't know. 9% seeing retirement as old. 3% define old age as becoming a grandpa or grandma. And 41% of the participants see old age as decline in physical ability. So part A mentions decline in physical ability, right? So we want to find out the sample is representative. In the sample, 41% of them define old age by a decline in physical ability. Then how do we determine the total number of Americans 25 years and older? How many of them define old age as decline in physical ability? We should use 41% to multiply by the population, right? What is the value of the population? 249,019,818. So to find a calculation that could give us the number of Americans 25 years and older who define old age by decline in physical ability, that's the formula. Okay. Part B, use rounding to find a reasonable estimate for this calculation. Let's say we don't have a calculator. If we do, then we can just multiply the two numbers together, right? But now we don't want to use a calculator. We want to just use the brain power and estimate. How do we do that? And we can use the tool of rounding, right? We use the tool of rounding. So firstly, 41%, I would round it to 40%, very convenient, right? And the population is a very inconvenient number. But as you can see, is pretty reasonable to round 9,019,818, because 9 million, right, is very close to 10 million. So very reasonable to round the 9 million up to 10 million and add the 10 million on top of the 40 million. So we're gonna round this number to 250. Yeah. So it had a 40 million here, but we run the 9 million up to 10 million. So 10 million add on top of 40 million gives us 50 million. So 250 million. You agree? Because this 9 here, right? So if we just round it up to 10 million, the error would be can be disregarded. And this would be very easy to calculate. 40% is 0.4, or we can write 40 over 100, right? And then we multiply 250 million. 1, 2, 3, 1, 2, 3 over 1. Yeah, there are different ways to process this operation. I'm going to cancel this 100 with those 2 zeros. Okay, and then 4 times 25 give me 100. And then I'm going to attach the rest of the zeros. We have 1 0 here. We have 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5. 5 zeros here. 1, 2, 3, 4, 5. 100 million. That makes sense, right? 40%. 40% of 240 million. 40% of 250 million is 100 million. 40%. Let's see. 4 times 25 is 100. Yeah, exactly. So that makes sense. Yeah, the result is 100 million. So in the population, among the population, around 100 million people, like adults 25 years old or older, have that definition for old age. Line graphs. Let's see this question. Line graphs is very popular. This actually is a time series. If we have the x-axis as time, and the line graph is also called a time series. Yeah, line graph, many line graphs have the horizontal scale as time. This is the case. As you can see, horizontal scale is time, vertical scale is the percent of college students. In 1982, 24% of the college students smoke cigarette or use cigarette. And 1990, the percentage dropped a little bit. And then 1998 go up, actually it's the peak. And then go down, go down, go down. And then 2020, the percent dropped to 8% only. 8% is only 1/3 of 24% in 1982. So that's what's going on in this graph. When we look at a graph, two-dimensional graph, you must at least look at the horizontal scale and the vertical scale. Understand what's going on in the graph, what information you can have. Now let's answer the 3 parts. Part A, find an estimate for the percentage of college students who smoked cigarettes in 2010. This is 2006, this is 2018. So 8 years apart. In the middle, we should have 2010. Yeah, 8 years apart. Half of 8 years is 4 years. So this is 2010. Go up and then go to the left. And see that is between 16% and 20%. I would say around 18% of the college students smoke in 2010. That's how do we understand the graph. Part B, in which 4-year period did the percentage of the college students who smoked cigarettes decreased at the greatest rate. If you have the algebra foundation, you might remember slope of a straight line describes rate of change, right? Describe rate of change. So which part of this line graph has the biggest slope? Here, when I say slope, I mean with absolute value, okay? With absolute value. Sometimes it could go up, so slope is positive. Sometimes go down, the slope is negative. And biggest, the greatest rate, decrease at the greatest rate. So we are looking for a part going down, and the slope has the biggest absolute value. Which part? I see this part, right? And that is from 2002 to 2006. 2002 to 2006. Yeah, feel free to pause the video and understand. Part C, in which year did 30% of college students smoke cigarettes? 30% is between that. Oh, that is 1998, right? 1998. It's pretty straightforward. Bar graphs. So here we have a multiple bar graph, actually. Multiple bar graph has more than one set of bars. As you can see from the legend, the red or purple, the red or purple represent the males, the yellow represent female. Horizontal scale times, years, and the vertical scale is life expectancy. So as you can see, the trend from 1950 to 2020, the life expectancy of males is getting bigger, it's getting up and go up. And females in general has a higher life expectancy, and the trend is also go up, but it's higher. Means in general, women live longer life than male. Part A, a man's increased life expectancy. So men, so look at the red bars, rounded to the nearest hundredth of a year for each subsequent birth year. Part A, we are actually looking for the annual increase in the life expectancy for male. Okay, for males. So we only look at the red bar from 1950 to 2020. In 1950, the life expectancy is 65.6, and then go up. By the end of 2020, the life expectancy of male is 77.1. So when you see this kind of problem, what do? This is what we do, okay? We are going to use the biggest value to minus the smallest value. We're going to use 77.1 to minus 65.6, and then divide the difference by the number of years. Let's see how many years from 1950 to 2020. Use 2020 to minus 1950. If you have a chance to go higher, take pre-cal or even calculus, there's a definition called average rate of change. So this actually is the concept definition of average rate of change. So from 1950 to 2020 is an increasing trend. So we use the life expectancy in 2020 to minus life expectancy in 1950, and to divide the difference by the number of years from 1950 to 2020. So this actually is delta y over delta x. If you are interested to know, is a very important concept in calculus or algebra. Let's do the calculation. Let's get a calculator. We use 77.1 to minus 65.6 and divide that difference by 70 years, right? And we need to round the number, round the value to the nearest hundredth. Nearest hundredth, remember, is to keep two decimal places. To keep two decimal places. And we have is around equal to 164. Oh, sorry. Let me erase that. Is 0.16. 0.16. The next digit after 6 is 4. Since 4 is less than 5, we round it down. So 0.16. How do we understand or interpret this result? It means, averagely speaking, every year since 1950, every year, the increase in man's life expectancy is 0.16 years. 0.16 year. Not exactly. Some years maybe bigger than that, some years less than that, but averagely speaking, there's 0.16 year increase in the male's life expectancy every year. Part B is to find the life expectancy of a man born in 2030. Obviously, we don't have 2030 in the graph, right? Yeah, 2030 is in the future. So one important purpose of finding the trend in statistics is to predict. So part B, we need to predict. We need to use the trend, the pattern we have just found, to predict the life expectancy for our man if he is born in 2030, right? Yeah. So suppose the trending is continue. Suppose the trending is continue. Means what? Means every year, if the trend continues, every year we have 0.16 higher, 0.16 year increase the life expectancy in male, right? Every year. From 2020 to 2030, that is how many years? That is 10 years, right? Then we can estimate that in the next, from 2020 to 2030, the increased life expectancy in male would be 1.6. And then we add 1.6 on top of the life expectancy 2020, 77.1. Add them together, we have 78.7. So we can say, we can use 78.7 as the estimate of the life expectancy of a man born in 2030. That's a prediction, estimation based on the trend and the annual increase in life expectancy of male. Right? So that's all the questions. I would say 1.2 is a little bit challenging. There's a few questions. So please feel free to email me if you have any questions. I'll see you next time.